also the concepts of normal distribution. Okay, so let's begin with this. Permutations and combinations. This is the next topic that we've got now. Now, first of all, we need to know something that we call the basic counting principle. That's something that will be used throughout this topic. Let's have a look at this example for that. We've got a menu for a restaurant here. We've got starters, main course, and dessert. There are 3 different starter options, 5 main course, and 3 dessert options. It says how many different 2-course meal options are there such that you choose a main course and dessert. How many options would you have in that case? Now you've got 5 main course options, you've got 3 dessert options. What's the total number of different combinations you can have in this case? With chicken, you can have any 3 of them. With steak, you can have any 3 of them. So what's the total that you get? 5 multiplied by 3, and that gives you 15. If you wanted a 3-course meal, that means you wanted a starter and a main course and also a dessert. For starter, we've got 3 options. We would say it's 3 times 5 times 3, and that's 45. It will be 45 different options that you can have if you choose a 3-course meal. From this, we basically, this is an example of something that we call the basic counting principle, and that says, if there is a certain number of ways of doing one thing, and if there's another number of ways of doing another thing, then if you were to do both of those things together, or you can say one after the other, they both mean the same thing, that number of ways is going to be their product. So if you have m ways of doing one thing, n ways of doing another thing, the total number of ways, when you were to combine those 2 things, that would be m multiplied by n. We would be multiplying those numbers. Okay, we'll be multiplying those numbers. Now, keep that in mind. You need to know about the concept of factorial, how factorial is calculated. For example, 6 factorial, that's 6 into 5 into 4, and so on for the other numbers. 0 factorial is 1. Now, in this topic, we'll be doing arrangements of objects, selections of objects, and so on. Let's start with some examples of that. So first of all, arrangements is a major part of this topic. A lot of questions that you will see on this topic, they will involve some kind of arrangement. Arrangement and permutations, these are synonyms. You can say that arrangement is the same thing as permutation, okay? Now, first of all, let's start with arrangements using factorials. Let's take some examples. Let's say we've got these 5 digits and we want to make 5-digit numbers from this. In how many ways can we do that? How many different 5-digit numbers can we make from this, given that the digits can be used more than once as well? Now, there is one representation that we'll be using a lot throughout this topic, and that's this boxes representation. We will represent the boxes to represent the places that some objects can have. So we've got 5 different digits here. We can say we can place those 5 digits in these 5 places. Okay, now how many options do you have for the first box? There are 5 digits. You can place any of them in the first box. You say it's 5 options. What about the second box then? Again, you can have 5 options for the second box as well. Why? Because the digits can be used more than once as well. You can have repetitions. You can have 5 again. You can have the same number again in the next box as well. So that's also 5. And then for the third, also 5, and so on. Using the basic counting principle, then we can say, if there are 5 ways of filling the first box, 5 of filling the second box, 5 of filling the third box, and so on, the total number of ways is going to be their product. 5 into 5 into 5 into 5 into 5. That turns out to be 5 raised to power 5, which is 3125. Now, if we were to change this slightly, and we say, the digits cannot be repeated now. The digits cannot be repeated. If digits cannot be repeated, what does that mean? How many options do we have for the first box? We've got 5 options for the first box, but then if we have placed 1 digit in the first box, how many options do we have for the next one then? Let's say we put 2 in the first box, then we only have the remaining 4 options for the next box. So that's only 4 options for the next one if the digits cannot be repeated. Then 3 for the next, 2 for the next, 1 for the next. We multiply all of them and we get 5 factorial for that. And that turns out to be 120. So logically, it's basically this, that 5 options for this, 4 for this, 3 for this. When we multiply all of them, it turns out that we can write that as 5 factorial as well. That's another way of writing the same thing. And that's the total result that you get, 120. There's 120 different 5-digit numbers that you can get from this, such that no digit is repeated. What about this? We've got 5 digits here, 1, 2, 3, 4, 5. And now we want to make 3-digit numbers from this, 3-digit numbers, given that the digits cannot be repeated. How do we think about this now? Now, this is not going to be factorial because the total number of digits is 5, and we want to make a 3-digit number from that. If you think about it logically, that means we've got 5 options for the first box, 4 for the second, 3 for the third. How many total number of ways do we have from this? 5 times 4 times 3, that turns out to be 60. Or as we will see later, we could also use this permutation notation here. We'll talk about this later, that we have 5 objects. We want to place them in, we want to arrange 3 of them. Out of 5, we have to arrange 3. So that's 5p3, that turns out to be 60. Okay. If the digits can be repeated, then for the first box, we have 5 options. For the second, we've got 5. For the third, we've got 5, because the same number could come again and again as well. And the total number of arrangements, that turns out to be 125, and that's your final result from this. Now, you could do this with letters as well. You could do this with letters as well. For example, you have these letters, M-A-T-H-S, T-H-S, and what you want to do is you want to arrange these 5 letters. You want to find the number of different ways in which you can arrange these 5 letters. And how many ways can we do that? We've got these 5 letters. We can't bring new letters from outside. So that means for the first box, we have 5 options. Now, the letters cannot be repeated here because we can't have, if we put one M here, we can't bring another M from outside. We only had one M. So the letters, all of them have to be different. What we do is we say it's going to be 5 times 4 times 3 times 2 times 1, 5 factorial, and that gives us the result. Okay, and you can see what that turns out to be. That's 5 factorial. Okay, now if you have repetitions, what happens in repetitions? Repetitions means you have some identical objects. In letters, for example, if you have the same letter coming twice, D and D, so you've got this word dad. In how many ways can you arrange the letters for this? You would say 3 factorial, but then you would divide by the factorial of the letter that is repeated. You have 2 D's, you divide by 2 factorial, and that gives you 3 from this. That's the number of arrangements that you get. In this case, there's a logic behind it. We don't need to go to that right now. The idea is, if you have some repeated objects and you want to arrange those objects, how can we do that? In this case, we've got 7 letters in total. In how many ways can we arrange 7 letters? 7 factorial. But then we have 3 i's, but divide by 3 factorial. Because of that, it becomes 7 factorial divided by 3 factorial, and that gives you the result. That's 840. Okay. You could have multiple letters that are repeated. For example, this word statistics, you've got S coming 3 times, you've got T coming 3 times, you've got I coming twice. The total number of letters that you've got is 10. You'd say 10 factorial, but then divide that by 3 factorial because of the S, 3 factorial because of the T's, 2 factorial because of the 2 I's, and that gives you the result. So when you have repetition in arrangement, what you do is you divide by the arrangements of those identical objects to get that result. That's the general rule, right? That's what we discussed. If you have some repeated letters, repeated objects, you divide by their factorials to get the total number of arrangements. Now, that's one thing that can happen. Then there can be different types of restrictions that you will see in problems. For example, let's take this case. You've got 12 books, 6 math, 4 physics, 2 chemistry. Now, all of these books are different books. They're not identical. So math books, for example, they could be P1, P2, P3, P4, and so on, right? These are different books. For physics as well, we've got 4 different books. For chemistry as well, we've got 2 different books. Okay, all of these books are different. Now, in how many ways can we arrange these 12 books? If there are no restrictions, we can say there are 12 boxes and we have to place 12 books in them. That's just 12 factorial, right? 12 for the first one, 11 for the second, 10 for the third, and so on. 12 into 11 into 10 into 9 into 8, and so on, all the way up to 1. That becomes 12 factorial. In the absence of any restrictions, we just do 12 factorial here. But then in arrangements, you could have a number of different types of restrictions. Now, what possible restrictions could you have? For example, you had 6 math books, 4 physics books, 2 chemistry books. If you want the chemistry books to be next to each other, so chemistry books should be together. They should be next to each other. Now, how do you handle that condition? So you had 12 boxes initially, right? You had 12 boxes like this. If you want the chemistry books to be together, the way to handle this is you merge 2 boxes and put the chemistry books in that single box so that the chemistry books would move together. They would not be separated, right? So you had 12 boxes initially. If you merge two boxes and put the chemistry books in that, how many total boxes do you have now? 10 other boxes, and then this merged box, right? You made one box out of two boxes, so that's 1. 10 plus 1, that's 11 boxes in total. In how many ways can you arrange these 11 boxes? 11 factorial ways. But then these chemistry books could also interchange, could also switch places. They're different from each other, right? So their arrangements also matter. So we say 11 factorial multiplied by 2 factorial. Okay, 11 factorial multiplied by 2 factorial, and that gives us the result. You can see what that turns out to be. This is what you get. Okay, now if you wanted the physics books to be together, there were 4 physics books. Again, we do something similar. We say, okay, we had 12 boxes initially, like this. We've got 12 boxes. What we do is we merge 4 of them. We merge 4 of them. And in that merged big box, we put the 4 physics books, P1, P2, P3, P4. In how many ways can we arrange this now? We've got 9 boxes in total, 8 remaining boxes, and this big box. That becomes 9 factorial. We can arrange these 9 boxes in 9 factorial ways. But then in how many ways can you arrange these physics books? You can arrange these physics books in 4 factorial ways. You multiply them, basic counting principle. You've got 9 factorial ways of arranging the boxes, 4 factorial ways of arranging this. The total number of ways is going to be their product, and that gives us this. Now, what about this? If all math books should be together, all chemistry books should be together, all the physics books should be together, how do you handle this case? Now, you say you've got 3 big boxes. In one big box, you've got all the math books. In another big box, you've got all the physics books. Another big box, you've got the 2 chemistry books. You've got 3 boxes now. In how many ways can you arrange these 3 boxes? 3 factorial. But then there are 2 chemistry books. In how many ways can you arrange them? 2 factorial. 4 physics, 4 factorial, 6 math, 6 factorial. Since all of the books are different, we just multiply them like this, and that gives us the result. Okay, so that there are no repetitions. Remember, the books are different. There's nothing repeated here. All the books are different. The C's are not the same. The P's are not the same. The M's are not the same. They're all different. Okay. All right. We'll talk about what happens in repetition when we do have identical objects, but for now, these are all different. The books are all different. Now, this is a case that is coming again and again in the recent papers. I'll slow down a little on this. You need to make sure that you understand this well. So the condition is that there are exactly 3 other books between the 2 chemistry books. Okay, that's the condition. So we've got 6 math books, 4 physics books, 2 chemistry books. They're saying there should be exactly 3 other books. They could be any of them. 3 other books between the 2 chemistry books. In how many ways can we have this arrangement that satisfies this condition? We can think of it like this, that we have 1 big box. Since we want 3 other books between the 2 chemistry books, that makes it 5 books in total. So we make a big box that has these 5 books. Chemistry books on the sides, okay? And in the middle, in these places, we could have 3 other books, okay? Now, how many boxes does that leave us with? 1 big box, 2, 3, 4, 5, 6, 7, 8. That's 8 boxes. In how many ways can we arrange these 8 boxes? 8 factorial ways. Okay, we can arrange these 8 boxes in 8 factorial ways. Now, these 2 chemistry books, since they are different from each other, they could also switch places. If they were identical, we would not do their arrangement, but in this case, they're different. So we'd have to arrange them as well. C1 and C2, they could switch places with each other. In how many ways can they do that? 2 factorial. And now what we've done is we've arranged these boxes, this big box, along with the rest of the boxes. The only problem is we do not know which books are going to be in these places between the 2 chemistry books. Which books would we have in these places? How do you do that? You could say you've got 10 remaining books. Under 10 remaining books. Apart from the 2 chemistry books, you have 10 other books. You could think of it like this. For this box, you've got 10 options. For this box, you have 9 options. For this box, you have 8 options. And that becomes 10 into 9 into 8. And that gives you the result. The outer boxes, we have already arranged. So we don't have to do that again. We don't have to arrange the books outside again. We've already arranged those boxes. That's already incorporated in 8 factorial. Only the inner part, this was not done. This part, so we can do it like this. We can say that's 10 into 9 into 8. Or another way of thinking about that could be, we've got 10 books. Out of those 10 books, we have to arrange 3 in these places. So we could do 10p3 instead of 10 into 9 into 8 as well. That's the same thing. We have to arrange 3 out of those 10 books in these places. Okay, now this is one method. This is one method that, yes, 10p3 is the same thing, yes. This is one method that would work. This is one method that would work if the remaining objects had no repetitions. Okay, so you had 2 chemistry books. Now the remaining books that we had, the physics books and the math books, they were all different. They were all different, right? If they were all different, we could use this method and this would work. However, if there was any repetition here, then we would have a problem. If there was any repetition amongst these books, then we have a problem, because then we would not know which books are here, because if you have the repeated books inside, then outside we could have some repetitions here. For example, let me give an example. So let's say the physics books, let's suppose they were identical. Let's suppose they were all identical. Now, in that case, we would have to know how many physics books are inside here and how many physics books are outside, because we would have to divide by their factorials in the denominator. And that would be a problem. That would be a problem, because you'll have to make a number of cases for that. You'll have to make cases like this, that one possibility is that you have 1 physics book inside, 3 outside, another that you have 2 inside and 2 outside, another that you have 3 inside and 1 outside. And that will be too many cases to make. For that, we have another alternative. We are considering that these 3 books could switch places. This is permutation. That permutation handles that, right? Permutation is considering their arrangements. We are arranging 3 out of those 10 books. So that switching is incorporated here, and also here when we multiply them, we're doing arrangements. That is already incorporated in this, okay? All right. What if we have repetitions? In that case, this method is not going to work. The more general method that for such problems is going to be this. That we think of it another way. We think of it like this. We say, again, we have 1 big box. We have 1 big box. And in that big box, we've got the chemistry books on the sides. Okay. And inside, we've got the 3 other books. Okay. And now we do not consider arrangements of the outer boxes. We do not think about boxes in this case. We think about the letters, the objects that are inside. So how many objects do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 places for these 10 objects. 10 places, 10 objects. And how many ways can we do that? 10 factorial. So for the remaining 10 books, those 10 books, we can just do 10 factorial, 10 factorial. Since they are all different, we don't have to divide by anything as well. But if there was repetition, we could handle that here now. So if the 4 physics books were identical, let's suppose, we could just divide by 4 factorial here, and that would, take care of it. In this case, they're all different. So let's just understand it using this example first, and then I'll show you another in which there is repetition. So 10 factorial for those letters, and then 2 factorial for the chemistry books switching places with each other. But notice, until now, we had this box fixed in this one place. This box could also move. This box could also move. This box could either be here on the left side. This box could either be here on the left side, or there could be another possibility that there was one box on the left side, one smaller box on the left side, and then that big box. And then 1, 2, 3, 4, 7. So we could have 6 boxes on the right side. This could be another possibility that the big box is in this place. Then another possibility could be that you have 2 boxes on the left side and 5 on the right side. That could be another possibility, and so on. How many cases like that do we have? Let's count them. One possibility is that it is in its current position. That's one possibility. Then how many other cases do we have? This is what these arrows represent. It could remain in its current position, or it could come here. That's 2. Its original position, and this, that's 2. 3, 4, 5, 6, 7, 8. You multiply this by 8. That big box could be in these 8 different places. Okay, that big box could go in these 8 different places. You have to know both of these methods. You have to know both of these methods. This is more general. That will work for almost all problems like this. The first one only works if there is no repetition. So you would only use this when the remaining letters, when the remaining objects, are not identical. Any of the remaining objects are not identical. Okay. Let's take another example of that. So what I'll do is I'll just get rid of these arrows for now. Let's consider this now. Now, in this case, the first method is not going to work, or if it is going to work, you have to make a number of cases for that. That makes that very inefficient. Let's consider that same method using this example. I'll do that again. How many different arrangements are there of the 11 letters in this word requirement, in which there are exactly 3 letters between the 2 R's? Exactly 3 letters between the 2 R's. How do you think about it? Now, these are letters. Letters, if there are 2 same letters, they're identical to each other. Okay. So what we can do is we can say, okay, there are 3 letters between the 2 R's. So we have one big box that has 2 R's on both sides. And then in the middle, in between those 2 R's, we've got 3 other letters. Okay. Now, let's think about these places: 1, 2, 3, 4, 5, 6, 7, 8, 9. In these 9 places, you would have these 9 letters, right? In how many ways can we arrange those 9 letters? We can arrange those 9 letters in 9 factorial ways. But then, how many of them are identical? 3. We divide by 3 factorial because of that. So for now, all we have done is we have arranged the letters inside the empty boxes. We have arranged these letters, these 9 letters in these 9 boxes. That's this 9 factorial divided by 3 factorial because of the 3 E's that we had there. But then this big box, this is one position in which it could be, that it could be on the extreme left. Another possible case could be that you have one box to the left of it and the others are on the right, and so on. You could have 2 boxes on the left and you have others on the right. You could have 3 boxes on the left and you have others on the right. So the idea is, how many different positions do we have for this big box? In how many other places could this big box be? It could be in its current position, or it could be here, such that this smaller boxes on the left of it. So that's another possible position. Another possible position would be that it's here with 2 small boxes on the left and the remaining on the right. So that's 3 in total, 1 original, and then these 2, 3, 4, 5, 6, and then finally 7. This big box could come in 7 different positions. So we multiply this number by 7. It's equivalent to saying you've got 9 factorial over 3 factorial. That's one case in which this big box is here. Another case would be in which that big box is such that there's 1 small box on the left side. Another case where you have 2 small boxes on the left side. So you have to add up all of these cases how many times? 7 times. So you can just multiply that by 7, and that gives you the total. That's 423360. You can doing this using the first method is very inefficient. That'll take too long. You'll have to consider cases. You'll have to consider cases like this, that there's no E inside, and there are 3 E's here. Then you can consider another case. You have 1 E here, and you have 2 E's here. Another case, you have 2 E's inside. You have 3 E's. You have 1 E outside. Another case where you have 3 E's inside and 0 E outside. You'll have to consider 4 cases. That will become too long. So I would not recommend that you do that. Okay, that will be too long. For 3 marks, that's a lot of work. You'll have to make cases in that case. You cannot do that directly because unless you know what is inside, you would not know what to divide by, whether to divide this by something or divide this by something. It would not be possible without making those separate cases. So that's why I'm saying knowing this method is important. Otherwise, it will become too long there. Why are we just multiplying by 7 and not 7 factorial? We have already considered the arrangements of these boxes. It's already done when we did 9 factorial. In 9 factorial, we have already arranged those letters, right? The 9 letters in these 9 boxes. We have already arranged them. If you do 7 factorial, that would again arrange these outer boxes. That will be double arrangement. We don't have to do that. We've already taken care of them. The outer 6 boxes, they're already considered. Their arrangements are already considered when we did 9 factorial here for these letters. These 9 letters come in these 9 places. So 9 factorial takes care of their arrangement. The only thing that is left is the possible positions of this big box. So this big box, this is the only thing that we are arranging now. We're not touching the rest of the boxes. This big box could go in 7 different positions. One its current position and 6 other positions. That's 7 positions in total. You multiply this by 7. Okay. All right. Let's move on. That's another case that you have to consider here. The rest of the questions at the end. Okay. Let's have a look at another case now. In how many different ways can we arrange these letters given that there are no restrictions? In how many different ways can we arrange these letters given that there are no restrictions? So we've got this word, Mississippi. If there are no restrictions, that's fairly straightforward. We say we've got 11 letters. That's 11 factorial. Divide by the factorials of the repeated letters. 4 factorial, 4 factorial, 2 factorial. That gives you the result. But then what if they say the 2 M's and the 2 P's and the M, they have to be next to each other. So 2 P's and M, they should be next to each other. They should be together. So what we do is whenever we want something to be, some objects to be next to each other together, we put them in a single box. So we put the 2 P's and the M in a single box like this. Okay. Now, what are the remaining letters? The remaining letters from that word are 4 I's and 4 S. In how many ways can we arrange this now? So in this case, we've got letters. So these are identical. These are identical. What's the number of arrangements that we get here? There are 9 boxes in total. That's 9 factorial divided by 4 factorial because of these 4 I's, 4 factorial because of the 4 S. That's the arrangement of these black boxes. But then inside this bigger box, we've got PPM. That's 3 letters in total. 3 factorial divided by 2 factorial because of the 2 p's that we've got here. We divide by 2 factorial because of that. Okay, and that gives us the result. You can see what that is. That's 1890. So if it was not books like before, if it was letters, then there's repetition. So we have to take care of the repetitions as well in this case. Now come the other kind of restrictions. Sometimes they want the objects to be separated. Sometimes they want the objects to be separated from each other. Again, the same scenario. We've got 6 math books, 4 physics books, 2 chemistry books. All of them are different. What we want to do is we want to arrange all of these books such that the chemistry books should not be next to each other. Chemistry books should not be next to each other. There are 2 chemistry books. We want to separate those 2 chemistry books. Now, how can we do that? One way to do that is that we say, let's find the total number of arrangements without any restrictions. That's 12 factorial because all of those books were different in this case. There's no repetition in this case. Subtract from that the case when the chemistry books are together, because once you subtract that case, in all the other cases, the chemistry books would not be next to each other. So we subtract the chemistry books together case from the total, and that will give us the result when the chemistry books are not together. Now, how do you find this, that the chemistry books are together? Remember, we did this earlier. There were 12 boxes initially. We merged 2 of them. That leaves us with 11 boxes. So that's 11 factorial. And then the chemistry books can be arranged in 2 factorial ways. We multiply them and we get the result from that. So that's what we do here. We subtract from the total 11 factorial into 2 factorial, and that gives us the result. Now, this is one way of doing this. You have to know this method. It's necessary for you to know this method. For separating 2 objects, we have another method as well. And that's something that you also have to know. You could also do it another way. And how's that? That is done using this method that we call the dashes and stars method. Okay. Now, what is it that we wanted to separate? We wanted to separate the 2 chemistry books. The 2 chemistry books had to be separated. And the remaining books, there were 10 books in total, right? Let's call them non-chemistry books. There's no condition on them. We don't want to separate them. We want to separate chemistry books, and we do not want to do anything to the non-chemistry books. Another way to think about that same question is that you have a representation like this, that you start with the dashes. The objects that you do not want to separate, let's start from them and make dashes for them. I'll summarize this later on as well. Start from the objects that you do not have to separate. So that's non-chemistry books. How many books are there? 10. So you have 10 dashes for them like this. You can make boxes here if you want. You can make dashes there. Making boxes separately, that's going to take time. So that's why we just use dashes in this case. In how many ways can we arrange these books? 10 factorial. 10 books, 10 places, that's 10 factorial. But now the chemistry books had to be separated. What we do is we say the chemistry books could come in these gaps between these books. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 gaps between these 10 dashes. There are 11 gaps in total. So now what about the chemistry books? The first chemistry book comes. How many choices does it have? How many options does it have? It has 11 choices, right? It has 11 options. So we multiply by 11. Then once one of those chemistry books is placed somewhere, for example, let's say this is C1, then the next chemistry book comes. How many options does that have? 10 options. So we multiply 11 and 10, and that gives us the result. That's the same thing as saying, when we do permutation notation later, you would realize it's the same thing as 10 factorial times 11 places. Arrange 2 books in those 11 places. That will be 11p2. So either of them, that will give you the result. That's the number of arrangements in which the chemistry books are not together. You have to know both of these methods, because sometimes you'll have to use the first one, sometimes you'll have to use the second one. In this particular example, both of them work. When you have to separate 2 objects, you can use the total minus together method. You can use the dashes and stars method. For 2 objects, both of them will work. Okay. However, Let's consider this situation now. We had 6 math books, 4 physics books, 2 chemistry books. If the question says, not all physics books should be next to each other. What does that mean? Not all physics books should be next to each other. Not all? What does that mean? There were 4 physics books in total. What that means is, all of them cannot be together. All of them cannot be together. However, it is okay if we had 3 books together. That's okay. There's no problem with that. It's also okay if there were 2 together and another 2 together, or 2 together and the other 2 separated. It could be any of those. That's okay. The only problem is you don't want all 4 together. How do you find this? You find the total number of arrangements. Subtract from that the arrangements in which all the 4 physics books are together, and that will be 9 factorial into 4 factorial. Okay, so that will give it the result. Total minus together, that will work in this case. Okay. But if it was different, if instead of not all, they said none of the physics books should be next to each other, what does that mean? None of the physics books should be next to each other. That means all of them have to be separated. All of them have to be separated. Even 2 cannot be together. Okay. Even 2 cannot be together, 3 cannot be together, 4 cannot be together. What about this now? Now, in this case, we cannot use the total minus together method because we'll have to find this, and this, subtract all 3 of them from the total. And finding this is relatively straightforward, but these 2, they're actually quite complicated to figure out. 3 physics books together, exactly 3 together, and exactly 2 together, they become quite complicated. So total minus together is not feasible here. If we want to separate all the objects, in this case, we use the dashes and stars method. How do we use that? We want to separate the physics books. So non-physics books, the remaining 8 books, they do not have to be separated. We start from those books that we do not have to separate. That's 8. So we make 8 dashes for them. 1, 2, 3, 4, 5, 6, 7, 8. In how many ways can we arrange them? 8 factorial. But then we've got 9 gaps between them. We had 8 dashes. Between those 8 dashes, we've got 9 gaps. In those 9 gaps, we have to now place those 4 physics books. Now, the first physics book comes, how many options does it have? 9. The second one has 8. The third has 7. The fourth has 6. And that gives us the result. Alternatively, you could say that's the same thing as 8 factorial times 9p4. That we have 9 places, arrange 4 physics books in them, 9p4, and that will give the same result. That's how you separate all objects like this. So in the previous case, when it says not all should be together, we use total minus together. In this case, where we have to separate all of them, we have to use 8 factorial into 9p4. Yes, that's equivalent to that. So 8p8 and 8 factorial, they are the same thing. So in general, npn is the same thing as n factorial, as we'll see later in a few minutes. So yes, you could do 8p8 as well instead of 8 factorial. That's the same thing. Okay, so how does this method work? You make dashes for the objects that you do not have to separate, and then make stars for the objects that you do have to separate in the gaps between those dashes. And you should know when to use which method. When it says not all should be together, when it's more than 2 objects, and we want that not all should be together, we do total minus together. When it says none of them can be together, in that case, we use dashes and stars method. For 2 objects, both of them work. For separating 2 objects, both of them have the same meaning and they work. But for more than 2 objects, you have to be careful. You have to know for sure whether this would work or this would work. You have to think about that. Okay. Not all means total minus together. None of means you use dashes and stars method. Okay, let's have a look at this now. Again, the same books. If the chemistry books have to be together and none of the physics books can be together. So now they can sometimes combine both the conditions as well. Some books have to be together and some other books have to be separated. some objects have to be together and some other objects have to be separated. How does this work now? So none of the physics books can be together, right? None of the physics books can be together. So what we do is we say, okay, physics books is what we have to separate. What is it that we don't have to separate? The remaining books. That's 8 books in total. So initially, we could make 8 dashes for them like this, right? 1, 2, 3, 4, 5, 6, 7, 8. However, we want the chemistry books to be together. If chemistry books are together, what we can say is let's merge 2 of these dashes so that we can place the 2 chemistry books in that single dash so that they remain together. Okay. In how many ways can we arrange this now? We've got 7 dashes. That's 7 factorial. Then these 2 chemistry books could switch places. That's 2 factorial. And then we've got 8 gaps between these dashes. 1, 2, 3, 4, 5, 6, 7, 8. So in these 8 dashes, we have to arrange 4 physics books. We can say 8p4. Or we could also say, for the first one, we have 8 options, then 7 options, then 6 options, then 5 options. You multiply all of them, and that gives you the result. Okay? So you have to know this dashes and stars method. Okay, let's consider that. That example is coming most likely. Let's have a look at this now. Now, this is a bit complicated now. So why did I say that having 2 out of 3 or 3 out of 4 together is going to be difficult to find? Let's understand that using this example. Find the number of different ways in which the 9 letters of the word green cage can be arranged if exactly 2 of the G's are next to each other. Now, how many G's do we have in total? We've got 3 G's here. 1, 2, 3. We've got 3 G's. If we wanted all G's together, that would be straightforward. We would put those 3 G's in one box, and then we could just find that, right? Like we used to do earlier. If they want exactly 2 G's together, that's a bit problematic. Why is that? Because if you were to, there were 9 letters in total, right? So you can make 9 boxes initially. So you have 9 boxes like this. And now, if you put the 2 G's in one box, you can say, let's put 2 G's in one box like this. Now, then you could say there are 8 boxes in total. So that's 8 factorial. Divide by any repetitions. E's are coming thrice, so we can divide by 3 factorial, and then for the G's inside, we could say whatever the arrangements are, they can't be arranged. So we could do something like this, but that would be wrong because the problem here is the total number of G's in this case is 3. If we do it like this, that we put 2 G's in one box, that's not going to give us the number of arrangements in which exactly 2 G's are together, because if we put them in one box, there is a possibility that the third G ends up coming next to them. And that would make 3 G's together. And that's not what we want. So putting exactly 2 G's together like this is not going to be as straightforward as this. Now, one way of thinking about this could be, we could say there are 3 possible cases that we could have. 1, we could have all G's together. Number 2, we could have 2 G's together and 1 separated. Number 3, we could have all of them separated. We want the number of arrangements for this middle case where exactly 2 of them are together. So one possible way of doing this could be, which is slightly longer, I will discuss a quicker way after this. But one way to think about this could be that you say, find the total number of arrangements. That's 9 factorial over 3 factorial and 3 factorial, because we've got 3 G's there and we've got 3 E's. This is what we get, the total arrangements. Subtract from the total arrangements when all G's are together. Subtract this case. Subtract this case. We have done that before. And subtract this case when the 3 G's are all separated. I'm sorry, I should have written them with a gap like this, where the three G's are all separated. Subtract this case. All G's together, all G's separated. Find these two, subtract them from the total, and that will leave you with this middle case, and that will be what you're looking for. Total minus together does not work because total minus together also leaves you with this option, right? Where all G's are separated. That's not what we want. We want exactly two G's together. We want exactly two G's together. So we can't have all of them separated. So that would not work. Okay. All right. So this is one way of doing this. We subtract from the total. We subtract from the total. How does this make sense? Because there are only three possible cases. We've got this possible case, all G's together. Second possible case, two G's together and one separated. Third possible case, all G's separated. These are the only three options that we've got. If we find the total, and we subtract from that this case and this case, what are we left with? The middle case, and that's what you want, right? We've got three possible cases. We know how to find two of them, but we want the third one, so we can subtract the two that we can find from the total, and that gives us that middle case. That's one possible case, the possible way of doing this. Now, another direct way of doing this would be like this. So what we want is, we want exactly two of these together. We want exactly two of these together. So we've got the word green gauge. We want exactly two G's together. Now think about the G's here. Think about the two G's here. The three G's here, sorry. The word is green gauge. We've got three G's and these six remaining letters. Right? We've got three G's and the six remaining letters. Now we want exactly two of these three G's together, and the ones should be separated. So we can consider it like this. We could say, let's put two G's in one box and put the third G in another box. And now, since we want only the case where exactly two G's are together, we want to make sure that the third G does not come next to these two G's, because that would make all three G's together. So we put two of these G's in one box and one in another box. And now what we want to do is we want to separate these two boxes. How can we do that? These are the letters that we do not want to separate. R, E, E, N, A, E. We make dashes for them. 1, 2, 3, 4, 5, 6. That's 6 factorial. But then we've got 3 E's that are identical here. We divide by 3 factorial because of that. So for these 6 letters, we've got 6 factorial over 3 factorial number of arrangements. And now, how many gaps do we have between them? 1, 2, 3, 4, 5, 6, 7. In these 7 gaps, we can arrange these two boxes in 7p2 ways, and that will give you this directly. That's 5040. That's another way of doing this, much more efficient. That's what you could do here. So if you want exactly two G's together, you put two G's in one box, put the third G in another box, and then you say you want to make sure that these two boxes do not come next to each other. And that will ensure that you have exactly two G's together and not three G's, and you will get that case like this. Okay. Other questions at the end? I'll answer that once you're done with them. This method will always work. This will always work. When you have 3 objects and you want to separate 2 of them, this should work. If you had 4 objects and they wanted that 2 are together and another 2 are together, you could make 2 boxes like this and separate them. If they wanted that 2 are together and the other 2 are separated, you could make 3 boxes like this and then separate them. Okay. We did not exclude the third G. That's also coming somewhere, but it's just not coming next to the other 2 G's. So for example, we could have a case like this where 2 G's come here and third G comes here. We have another letter in between them, one of these 6 letters. So that ensures that we don't have all 3 G's together. We have only 2 G's together. 4 from 3? What does that mean? Okay, there's a Zan going on here. We'll have a 1-minute break. Other questions, I'll be answering them at the end. Let's move on after this. Keep a note of your questions. I'll answer them towards the end, okay? Are you sure about it? Is this credible news? या बस वैसे rumors चल रहे हैं? Trump would be mad. The kind of ego that he has, he would not like it. Where is it coming from? Okay. Why are we not dividing by the repetitions? There's no repetition here. This box has 2 G's in it. This has 1 G in it. These are different boxes. These are different objects. This is a different object. This is a different object. So we don't have to divide by anything. If we're talking about arrangements of the 2 G's, that doesn't matter. They're identical to each other. So why would we arrange them? These are identical to each other. Even if we were to arrange them, we would say 2 factorial, but then both of them are identical. We divide by 2 factorial. It doesn't make any difference. Now, within box, of course, they're identical, so they're not going to be arranged. Yes, so if both of the objects were identical, so if we had, for example, a G and another G, then yes, we would have to divide by 2 factorial in that case. Or if we had a box like this and another box like this, then we would divide by 2 factorial as well. But these boxes are different from each other, so we don't have to do anything. Okay, all right, let's move on. Let's look at this example. This is pretty straightforward. So you talked about most of the cases that you would get in arrangements. Let's have a look at a couple of questions on this. Then we move on to permutations, combinations, notations. Let's say you've got this word Argentina. It includes the 4 consonants R, G, N, T, and 3 vowels A, E, I. Find the number of different arrangements of all the 9 letters. That's fairly straightforward. But then the number of arrangements in which we have a consonant at the beginning, then a vowel, then another consonant, and so on alternately. Again, another case that you will see frequently in the recent papers. Consonants and vowels are coming alternately. So the first has to be a consonant. They said that you have a consonant at the beginning. If they had not said that, we would have to consider 2 possibilities. It starts from consonant or starts from vowel. In this case, they have told us that starts from consonant. So that means this has to be a consonant, this has to be another consonant, then C3, C4, C5. And in the gaps between them, we've got the vowels. There are 4 vowels in total, V1, V2, V3, V4. Now, in how many ways can we arrange the consonants? There are 5 of them, 5 factorial, but then 2 of them are identical, N and N, we divide by 2 factorial because of that. And then the vowels, there are 4 of them, that's 4 factorial, but A's are identical, we divide by 2 factorial because of that. Multiply them and we get the result from that. That's 720. Okay. All right. Let's move on to the next one. That was part 2. Okay. So this is a case now where you have to make, this is an example now where you have to make multiple cases sometimes. So let's look at this example. It says, find how many different 4-digit numbers can be made using only the digits 1, 3, 5, and 6 with no digit being repeated. Now, the first part is fairly straightforward. That's just 4 factorial, that's 24. The second part, I'm just going to focus on that. The second part of this, find how many different odd numbers, what I'll do is just get rid of this here. Find how many odd numbers greater than 500 can be made using some or all of the digits 1, 3, 5, and 6 with no digit being repeated. Now, how do we think about this? We've got 1, 3, 5, 6. These are the 4 numbers that we've got. They cannot be repeated. The number has to be greater than 500 and it should be an odd number. Now, how do you think about this? Greater than 500, it could be a 3-digit number, it could be a 4-digit number. So we have to consider both of those possibilities, 3-digit and 4-digit. Now, let's start with 3-digit first of all. If it's a 3-digit number, if it's greater than 500, then the first number, the first box, so we have 3 boxes, right? The first box could either be a 5 or it could be a 6. Only then the number would be greater than 500. And it has to be an odd number, so the last digit, it has to be either a 1 or a 3 or a 5. But now we've got a problem. Because if you have 5 in the first box, if the first box is a 5, then the last box, how many options would that have? Only 2 options. If the first box is a 6, then the last box would have 3 options. So depending on what you have in the first box, the number of ways that you have for filling the last box, that changes. So we cannot do it directly. There's no way to do it directly. We would have to make multiple cases for this. Okay, because there's ambiguity. So if we say there are 2 options for the first box, there are 2 ways of filling the first box. What about the last box? We have to first fill the boxes that have some conditions in them. So what boxes have conditions? The first box, because that will ensure that the number is greater than 500. If the first number is, the first digit is 1 or 3 in a 3-digit number, the number would be less than 500. We don't want that. So for the number to be greater than 500, the first digit has to be either a 5 or a 6. So we have two ways of filling the first box. But then if it's an odd number, how many ways do we have for filling the last box? Now, it depends on what we have in the first box, because if we have 5 in the first box and the last box has only 2 options, 1 and 3. If we have 6 in the first box, then the last box has 3 options. That's 1, 3, 5. So what we have to do is we have to break it into 2 parts, make 2 different cases for this. One case in which we say the first digit is a 5. In that case, the last digit could either be a 1 or it could be a 3, so that the number remains an odd number. That's one possible case. So in how many ways can you do this now? Now 5 is fixed. We can't change that. For the last box, we've got 2 options, and then we have 2 digits left. They could come in the middle box. So 2 times 2, that is 4 for the first case. You start from the box that has some condition on them. You start arranging those objects or those places that have some condition. So condition is on the first box and the last box. So first of all, you have to arrange those boxes. First is a 5. That's only 1 option, right? Last could be 1 or 3. So we've got 2 options for that. Once we fill the last box as well, for the middle box, we have 2 options left. That becomes 4 in total. The second case would be that the first digit is a 6. In that case, the last digit could either be a 1 or a 3 or a 5. So that means in this place, we have 3 options. And then we have 2 left for the middle box. That's 2 into 3. That becomes 6. These are 2 possible cases. And the third possible case would be that you have a 4-digit number. If it's a 4-digit number, that's necessarily going to be greater than 500, right? It will always be greater than 500. So there's no condition in the first digit then. The only condition is on the last digit. The last digit could either be 1, 3, or 5. We've got 3 ways of filling that. And then once we have done that, for the remaining 3 boxes, we've got 3 digits, 3 boxes. That's 3 factorial, or you could say one of them has 3 ways of filling, the other has 2, and the other has 1. That's 3 into 2 into 1. That's equivalent to 3 factorial. And that gives us 18. Add all of them up, because it could either be this case or this case or this case. There's an or between these cases. We add all of them up and get the total result from that. So sometimes what we have to do is we have to make cases like this. Okay, we cannot do it directly. We have to make cases like this. Makes sense? Makes sense? Yeah, this is tricky. It requires a lot of practice, Of course, you have to, these are standard methods that we're doing. But then once you've done all of these, then out of the 10 marks, 7, 8 marks generally are going to be fairly straightforward. Once you have practiced these enough. In permutation combinations, enough practice means like 70, 80 questions. Right? So you should have done at least that much until now in total before the exam. Why can't we take 6 in the first box? We considered that option, right? We had to make that as a separate case. Okay, let's move on. Okay, so we've been talking about arrangements. The topic name is permutations and combinations. What are permutations? What are combinations? We haven't even talked about them. Permutations, as I said, is another name for arrangement, right? So now we used factorials until now for all of those arrangements. Where do permutation notations come in? Let's think about this. So permutations is another word for arrangement. Let's consider this scenario. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. How many 6-digit numbers can we write using these 9 digits so that no digit is repeated? Now, earlier we could think of it like this. That it's a 6-digit number. So the first box could have 9 options, right? Any one of these nine digits could come in this place. The second has 8 options. The third has 7 options. The fourth has 6 options. The fifth has 5 options. And then this one has 4 options. You multiply all of them and you get 60,480 from that. Alternatively, you could do it directly like this. You could say there are 9 objects. You want to arrange them in 6 places. That's 9p6, and that gives you 60480. You could do it directly using permutation notation. So what does this notation mean? 9p6 means arrange 6 out of 9 objects. In general, we could say NPR, that means arrange R out of N objects. That's what this notation means in general. Okay. This is the formula for this, but that's not very important for now. Let's consider this situation. We have 15 people who walk into a room with 9 chairs. How many different seating arrangements are possible for them? We've got 15 people, 9 chairs. We have to arrange those 15 people, arrange 9 out of those 15 people. That's just 15p9. If we have 9 people and 15 chairs, so it's the other way around now. 9 people and 15 chairs, and we have to arrange these people. We just change our perspective. So earlier we were thinking of it like this, that for the first chair, you have 15 options. For the second chair, you have 14 options. For the third chair, you've got 13 options, and so on. So that becomes 15 into 14 into 13 and so on, all the way up to 7. That's 15p9 directly. Out of 15, arrange 9. This is just the other way around. You are thinking of it like this. The first person has 15 options. The second person has 14 options. The third has 13 options, and so on. This also ends up being the same thing. That's 15p9. Now, I won't go into detail about this. You can find that in one of those videos in which I've explained this. But the takeaway from this discussion is, whenever you are arranging objects, so let me just show you the results from this directly. We had 15 people, 9 chairs, 15 objects, and 9 places. 15p9 is the number of arrangements that we get from that. If we switch that, the number of people, the number of objects, if that's less, and the number of places, that's more. Again, if you want to arrange them, whatever is the bigger number that comes here, whatever is the smaller number that comes here, that's also 15p9. If that number is equal, 15 people walk into a room with 15 chairs, and that means just 15p15. And that's equivalent to saying 15 factorial. That's equivalent to 15 factorial. When the number of places and the number of objects that's equal to each other, you could use factorial as well in that case. So the result from that is, whenever the number of objects and the number of places that are equal to each other, in that case, we can use 9 factorial. For example, if we have 9 objects, we want to arrange them in 9 places, we say 9 factorial. If we've got 7 objects, we want to arrange them in 7 places, that's 7 factorial. We could also say NPN, right? We could say 9p9 for the first example that I said, 7p7, they're the same thing. In this case, you could use any of them, factorial or this permutation notation. However, when the number of objects that you're arranging is not the same as the number of places, when these two are not the same, in that case, we use the permutation notation. We say NPR. Whatever is the larger number that comes on top, whatever is the smaller number that comes here, and that gives you the result. Okay. So when this is not the same, in that case, you use this permutation notation. You've done this before in the examples that we looked at earlier in arrangements. For example, here, for instance, we had 8 places for these physics books, 9 places for these physics books, and we had 4 of these books. We just said 9P4, right? That gave us that result directly. So that's the idea. You can use permutation notation. You can use permutation notation to calculate this directly like this using NPR notation. Okay. Now there's a logic behind it where this comes from. So this is the formula. NPR is n factorial to n minus r whole factorial. So when you multiply those individually, like we did here, 9 into 8 into 7 into 6 into 5 into 4, this permutation notation actually does that exactly same thing. You end up with the same result as that, but you can just put this on a calculator directly as 9P6 and you would get the result. You would not have to do all of this manual work in that case. Okay. But again, that's out of the scope of revision right now. The second thing is combinations. How many permutation questions come in the exam? Sometimes 1 big question, sometimes 2 relatively smaller questions. You can say 10 to 12 marks. 10 to 12 marks. Sometimes the probability question that you get, and that as well, you can use combinations, although it's not required. There are going to be alternatives as well, but the simpler way of doing those questions sometimes is going to be using combinations. So you can say 10 to 12 marks minimum 10 to 12 marks. Okay, out of which 7, 8 are going to be relatively easier. For the remaining, you would have to think more. But 7, 8 are generally going to be relatively easier if you have covered all the basic concepts, all these standard methods. If you know all of these standard methods, these are all standard methods that you would need to know. Then 2 out of those 3 parts are generally going to be fairly straightforward. If you have done all of these efforts before, then they're going to be straightforward. And then for 1 part, in some very difficult questions, you would have to think a bit more that you have to do in the exam. That will depend on how well you've practiced and how well you understand the concepts. But 7, 8 marks generally going to be relatively easier to figure out. The second thing is combinations. Now, combinations is when you are selecting some objects and the order is not important in that case. So we're not arranging them. We're just selecting objects without caring about the order. Okay. Now, the keywords that you would see in this case would look like this, that you have to select objects, you have to choose objects, you have to make a group of something, you have to make a team of something. All of these mean we're talking about combinations, because in this case, in these cases, arrangements don't matter. Okay. Let's take some examples. Let's say we've got this. How many different teams of 2 people can be made from 3 people, A, B, and C? We just say 3C2 in this case, that gives us 3. Now, what's this notation? NCR, this means select R out of N objects. Select R out of N objects. Now, if you were to arrange them, that would be 3P2, and that's 6. Those 6 arrangements would be like this: AB, BA, AC, CA, BC, CB. But when you're selecting objects, the order does not matter. So these 2 are going to be the same. These 2 are going to be the same. These 2 are also going to be the same. So in combinations, you only have these 3 cases. There are 3 different possible selections that we've got for this. Okay, so for that, we do 3C2 like this. Now, this is something important. This is the relation between permutations and combinations, how they're connected to each other. NPR, that means arrange R out of N objects. Now, while it works, it basically does 2 things. When you say arrange R out of N objects, that means you have to select R out of N objects and then arrange those R objects that you've selected. So we could say NPR, therefore, is the same thing as NCR, that you select R out of N objects, and then you arrange those R objects arranging R objects as just R factorial. So that's the relation that we've got between permutations and combinations. Why is it important? Because sometimes you will see, as we'll see in some examples, you have to do arrangement, but you end up having to use combination there as well for arrangement. Why would that be? Because there would be some condition on selection that they would have applied. For example, if there are 10 people and there's some condition on selection that there are two brothers who should both be selected or should both not be selected. Now, if there's some condition, then you have to, in condition on selection, you first have to apply combinations to select, applying those conditions. And then if you had to arrange those selected people, you would do arrangement separately. So sometimes it's an arrangement problem and you have to do combination first of all, and then do arrangement afterwards because of that extra condition that might be there sometimes. I'll show you some examples of that. Let's have a look at this. How many different teams of 3 people can be made from 4 people, A, B, C, and D? That's fairly straightforward. We want a team of 3 people. There are 4 people, 4C3, that turns out to be 4. Now, if it says a delegation of 3 boys and 4 girls is to be selected from a class consisting of 10 boys and 15 girls, how many different delegations can possibly be selected? Again, we're talking about selections, that's combinations. We want 3 boys out of how many boys? Out of 10 boys, so that will be 10C3. 4 girls out of 15 girls, that's 15C4. So this turns out to be 10C3 times 15C4. Multiply these two and that gives you the result. That's 163,800. Okay. Select 3 out of 10 boys and select 4 out of 15 girls. You multiply both of them. Let's have a look at this now. There's a group of 12 people, 8 boys and 4 girls. We need to arrange 3 boys and 2 girls from this group in a straight line. In how many ways can this be done? Now, you see, there's a condition. There's a condition that there have to be exactly 3 boys out of those 8 boys, and there are 2 girls out of those 4 girls. Now, we cannot directly do this. It's arrangement. Arrangement means we're talking about permutations or factorials. We have 12 people. We have to select 5 and then arrange them. 12p5 would not work because that would not ensure that there are 3 boys and 2 girls. 8p3 times 4p2 would also not work because that would mean you are arranging the 3 boys separately and the 2 girls separately. That also does not work. They don't want them to be arranged separately. Those 5 people have to be arranged together. So how do you deal with this? Now, first of all, you take care of that condition that's given. The condition is you want to select, you want 3 boys out of 8 boys, that's 8C3. And you want 2 girls out of 4 girls, that's 4C2. Once you have selected these 5 people, this is how you select those 5 people. Once those 5 people are selected, then you have to arrange them. In how many ways can you arrange 5 people? 5 factorial, you multiply by that. So it was an arrangement problem. However, there was some condition on selection first of all. So we first handle that condition using combinations, and then we multiplied them. Okay. Yes. So when there's an or between cases, we add them. When there's an and, we multiply them. Make sense? Okay. Let's move on. Let's consider this now. There are 5 people, A, B, C, D, E. You need to select 3 of them for a competition. What's the probability that a randomly chosen team would have B in it? Now, sometimes they ask you for probability like this as well. Now, we have done probability already. That's number of favorable outcomes divided by the total number of possible outcomes. Probability can come with permutations and combinations as well. In this, the formulas would look like this. If it's permutations, we can say number of favorable permutations divided by the total number of possible permutations. If it's combinations, we could say number of favorable combinations divided by the total number of possible combinations. So we can find probability in combinations and permutations like this as well. Let's look at this example. There are 5 people, A, B, C, D, E. You need to select 3 of them. for a competition. Now, 5 people, they're all different. We have to select 3. That's just 5C3. Okay. If there was no restriction, the possible selections would be 5C3. Now they're saying, find the probability that a randomly chosen team would have B in it. So that means B should be selected. B should be selected. What does that mean? B must be selected. If B must be selected, we can say there are 3 places in the team. 3 people have to be selected. So there are 3 places. If B has to be there, then 1 place is already occupied by B. How many options do we have for the remaining people now? We've got 4 people left. Out of those 4 people, we have to select 2. So that's 4C2. And that turns out to be 6. So the number of possible teams in which there is B, that is 6. What's the probability going to be? 6 divided by the total, which is 5C3. That's 10. 6 over 10, that gives you the result 3 over 5. That's the probability that we were looking for. So you can find probability like this as well. Find the number of favorable combinations, the combinations that satisfy the condition, divide by that by the total number of combinations, and that gives you the result. Sometimes it can become a bit more complicated. For example, what if you got this? In how many ways can you select 3 letters from A, B, C, D, E? Now, in arrangements, when we had repetitions and we had to do arrangement, we used to divide by the factorials to, handle those repetitions. So in this case, if we had to arrange this, we would say 6 factorial divided by 2 factorial. We used to divide by factorials to handle repetitions. In combinations, there's no direct way of handling repetitions. In combinations, whenever you have identical objects or repeated letters, you always have to make cases. You have to make multiple cases for the repeated letter. For example, if they want you to figure out the number of ways in which you can select 3 letters from A, B, C, D, E. Now, the problem is the A's are repeated here. We cannot directly do 6C3. That would not work because we haven't got 6 different letters there. These are 4 different, and then there are 2 identical. Okay, that would not work. In repeated, that combination notation only works if all of these objects were different. So what do we do then? We have to make cases for this. A's are repeated, so we consider the possible cases for A. One possible case could be that there is no A, and we have to select 3 letters. So out of the remaining 4 letters, we have to select 3. That's 4C3. That turns out to be 4. The second possible case would be that there is 1A. So 1A is selected. Now for the remaining 2 places, we've got 4 options. So 4C2, that's 6. And then the third possible case could be that we have 2 A's. So we have 2 A's here. And then for the third place, we've got 4C1 option. That's 4. It's either the first case or the second case or the third case. We add all of them up, and that gives us the result. That's 14. And that's our final answer. Okay. So in combination, when you have repetitions, you have to make cases. You cannot do it directly. Sometimes you can have multiple letters that are repeated. For example, like this. You've got A, B, B. You've got 2 letters, 2 objects that are repeated like this. You have to select 4 letters from this. Now you have to make cases for both of them. You have to make cases for A and B. Both of them are repeated here. So what would be the total cases? Figure out what happens if we have 0A, 0B. 0A, 0B is not possible because in that case, you only have 3 other letters left, right? C, D, E. We can't have 4 letters out of 3. So that would not work. So we want at least one of them. So one possible case would be with 0A, you can have 1B, you can have 2Bs. With 1A, you can have 0B, 1B, 2B. With 2 A's, you can have 0B, 1B, 2Bs. These are all the possible cases that we've got. These are all the possible cases that we've got. Okay. Now, for the first one, we say there has to be 1B. So 1B is already there now. It doesn't matter which one of them is there. It doesn't matter which one of them is there because the letters are identical, right? So it doesn't matter if it's this B or this B. It does not matter. It could be any of those B's. So we don't have to select the B's out of this in this case. For the remaining letters which are different, we say that's 3 letters remaining. We have to select 3 of them. That's 3C3. All right. Then if we want 2 Bs, then you have 2 remaining places. Out of the remaining 3 letters, we have to select 2. That's 3C2, and so on. We have all of these cases. For example, here we have 1A, 2 Bs. That means we've got 1A, 2 Bs already there. For the one remaining place, we have 3 options, C, D, E, 3C1. That will be this. Find all of these cases like this, add them up together, and that gives the result. That's 18 total different selections that are possible from this, in which we have 4 letters. Okay. Now, for the identical letters, we don't choose from them because it doesn't matter whether it's which A it is. It doesn't matter. When we're finding number of selections, that does not matter. Okay. So in combinations, identical objects cannot be handled directly. We need to make multiple cases for the identical object to find the total number of possible combinations. We cannot handle them directly like we used to do in arrangements or permutations. In combinations, that's not possible. Let's consider this scenario. This is another possible case, that possible type of question that you will see. So Jeff wishes to plant 25 flowers in a flower bed. He can choose from 15 different geraniums, 10 different roses, 8 different lilies. He wants to have at least 11 geraniums and also the same number of roses and lilies. Find the number of different selections of the flowers that he can make. So in a lot of combination questions, you have to make cases like this as well. You've got 25 flowers in a flower bed. You've got 25 flowers. Okay, so you have to plant 25 flowers. You've got 15 geraniums, 10 roses, 8 lilies. Okay. Now, the total number has to be 25. There should be at least 11 geraniums. So now you have to make the different cases that are possible for this. So one case is we've got 11 geraniums, and then the number of roses and lilies, they have to be the same. So the remaining are 14, 25 minus 11, that's 14. So these are 7 and 7, that's one possible case. Another possible case would be that you've got 13 geraniums. 12 is not possible because if we have 12, then the remaining are 13. They cannot be equally divided. We want the same number of roses and lilies. So 12 is not possible. We have 13 geraniums. In that case, the others will be 6 and 6, 15. The others will be 5 and 5. And now we say the first case is out of the 15 geraniums, we have to select 11. Out of 10 roses, we have to select 7. Out of 8 lilies, we have to select 7. That's 15C1 into 10C7 into 8C7, and that gives us the result. Similarly, you do the next one and the next one. In this case, all the flowers are different, so we have to select from all of them, right? We have to select from all of them. In the previous case, you were talking about letters, and letters, these were identical letters, so we did not have to choose for them. Okay, they could be, their selection would not matter because they were identical to each other. Okay. So we'd have cases like this as well, in which you have to, make a table-like structure like this and then find the combination for them. No, the question says that it has to be the same number of roses and lilies. That's the condition in the question. Okay, all right. If there was no condition, then of course we would consider that as well. Let's consider this. 5 of the 11 letters in the word requirement are selected. How many possible selections contain at least 2 E's and at least 1 R? Okay, how do we think about this? Again, we're talking about selections, combinations. We've got repeated letters here. Some letters are repeated. So we have to make cases for whatever are the repeated letters. Which letters are repeated? R's are repeated and E's are repeated. So we have to make cases for them. Now, the condition is at least 2 E's and at least 1 R. What are the remaining letters which are not repeated? These letters, there are 6 of them. Q, U, I, M, and T. Okay, so what are the possible cases now that satisfy these conditions? 2 E's, 1 R, that's one case. So we have 2 E's and 1 R already there. We have to select 5 in total. So we have 2 places left. Out of the remaining 6 letters, we say, let's just select 2, that's 6C2. Okay, and that gives us a result. And then for the second case, another possible case could be with 2 E's, you could have 2 R's. That's 4 letters already selected. For the remaining 1 place, you have 6 options. So 6C1, that gives you another value. Similarly, for the rest of the cases, 3 E's, 1 R, 3 E's, 2 R's, add all of them up, and that gives you the result. You can see what that is. Okay. Now in this question, so this is the general way of doing this. This is the general way of doing this. Okay, that will work for any question like this when they talk about number of possible selections. When they talk about number of possible selections, this is the general way, general method that would work in such problems. But in this particular case, for those of you who are who have practiced well and are good at this topic, there could be a more efficient way of doing this in just one single step. Since combination does not work when you have repeated letters, in this case, the conditions are like this. They're saying there should be at least 2 E's. Okay, so we have 5 letters that we have to select. We've got 5 letters that we have to select, right? 1, 2, 3, 4, 5. They're saying there should be at least 2 E's. That means 2 E's have to be there no matter what. At least 2 E's have to be there. And at least 1 R has to be there. So at least 1 R has to be there. Now, if we get rid of 2 E's and 1 R from this total number of letters, what are we left with? 2 E's and 1 R. So we have R, E, Q, U, I, M, N, T. Right? I've gotten rid of 2 E's and 1 R. And that leaves me with this. Now, all of these letters you see in this case, in this particular case, are different. These are 8 letters in total. Out of these 8 letters, now since we know that these 3 have to be selected, out of those 8 letters now, we have to just select 2. We could directly do 8C2 here, and that will give us 28. That will be a 4-mark question. You could just do this, 8C2, 28, and that's it. That's your final answer. But that only works in this case because of the condition that's given. The condition is such that when we have 2 E's and 1 R, the remaining letters are all different. So we could just use combination directly on this. So yeah, that will work. That will be, I think, at least a 4-mark question. You could write that directly like this, and that will be fine. Okay. If you get that, that's great. Otherwise, this is the general method that will work for every kind of question like this. You make cases for the repeated letters. Okay. Now, this is important. A very similar question, but we do it differently. In the previous case, we were talking about number of possible selections that contain at least 2 E's and at least 1 R. Number of possible selections. Now, in this case, we're saying, find the probability that the selection contains at least 1 O and at least 1 R. Okay, now how do we think about this? 4 letters are selected at random from these 8 letters in the word tomorrow. Find the probability that the selection contains at least 1 O and at least 1 R. Now, 4 letters. What could be the 4 letters that you could select? The problem here, let me just quickly tell you about the logic behind it. Then if you understand it, that's good. Otherwise, I'll tell you what to remember. One possible selection of the letters could be satisfying this condition. You could have T, O, M, R. This is one possible selection. Okay. Another possible selection would be T, O, O, M. Now, these are 2 different possible selections. Their probabilities are not the same. Their probabilities are not the same. Why are the probabilities not the same? After permutation and combinations, it'll take, I think, around 15 more minutes, 15, 20 more minutes. After that, we'll have a break. Okay, so consider these 2 possible cases. Possible selections, TOMR and TOM. Okay. Now, these 2 do not have equal probabilities. Why? Because we've got 3 O's. So probability of getting 2 O's is more as compared to getting some other letter twice. Since some letters are repeated, probability of selecting an O from this 8-letter word is more as compared to selecting a W, for instance. Probability of each outcome is different. Since the probability of each outcome is different, if we were to do it directly like this, the probability formula, remember, that would not work. The number of favorable outcomes divided by the total number of possible outcomes, that formula, as we discussed in probability, assumes that each outcome has equal probability. So we cannot do it like this, that we find the number of selections like we did here in the previous case. Divide that by total number of selections. That would not give you the correct result. So how do you handle this? How do you handle this? Whenever you have a probability problem, whenever you have a probability problem, in order to use that formula, number of favorable outcomes divided by the total number of possible outcomes, the condition is the outcomes need to have equal probabilities. In this case, because of these letters being repeated, some letters have more probability of selection as compared to other letters. So what we do is, whenever we have probability and combinations and there is repetitions, whenever these three conditions are met, you have to memorize this now, okay? Whenever you have probability, combinations, repetitions, okay? Probability, combinations, and there is something repeated in that set of objects, set of letters, you treat all letters as different. You treat all letters as different so that you equalize their probabilities. So you consider it like this, that this is O1, this is O2, this is O3. This is R1, this is R2. So treat all of them as different objects, okay? Then you handle it like you handled this flower case earlier, right? So you do it like this, you say, okay, if all of those letters are different, then we could just use combination notation directly. 8C4, out of 8 letters, we have to select 4, that's 70. That's the total number of possible selections that we could get in this case. 8C4, that's 70. And then how many of them satisfy the condition? We make cases for them. There are 3 O's. Remember, we're considering all of them as different. We're considering all of them as different. There are 3 O's. There are 2 R's. And there are 3 remaining letters. Let's merge them together as well. There are T and W. They're all different. That's the third category of letters that we've got. Now, what's the condition? We want at least 1 O and at least 1 R. So make cases for them. Total number should be 4, 1, 1, 2, 1, 2, 1. Now, do it in a structured way. Fix 1 and then change the others. For example, you could do something like this. With 1 O, what are the options that you can have? 1, 2, 2, 1. And then with 2 O's, what are the possibilities? 2, 1, 1, 2, 2, 0. With 3 O's, you could have 1, 0, right? These are all the conditions, all the possible cases that satisfy both of these conditions. You find their number of selections. Now, in this case, you see what's happening. We are doing 3C1. We're doing 2C1 as well, because we are treating these letters as different. So we have to select those letters as well. In probability, in combination problems, you have to select those repeated letters as well. When we just find number of selections, in that case, we don't do this, okay? So you find all of those cases, add them up together, that gives you 50. 50 divided by the total number of possible combinations, that's 50 over 70, that's 5 over 7, that's the probability that you get from this. This is coming a lot in recent papers. You need to remember this condition. Probability, combinations, repetitions. When these 3 conditions are met, treat the letters as different categories. Okay. All right, let's move on. So hopefully we'll be ending in 10-15 minutes, inshallah. Hopefully around 10 minutes. Okay, so that's a lot. I hope you've gone through this earlier already, and it's not the first time that you're doing this. Just then it will be a lot of work over the next few days then to practice this as well. Okay, let's have a look at this now. We have some people who are taking a photograph. The members will stand in 2 rows with 5 in the back row and 4 in the front row. In how many different ways can 9 members be divided into a group of 5 and a group of 4? We want to divide people into groups. What's that? That's combination, right? We're making groups of people. Order does not matter here. How can we do that? There are 9 people in total. How many groups can we make out of them? How many possible different groupings can be there? We can say out of 9 people, make a group of 5, that's 9C5. And then out of the remaining 4 people, select 4, that's 126. Now, once you have selected 5 people, it's understood that the remaining 4 people are going to go into the other group. So if you just do 9C5 in this case, that will also give the same result. 4C1 is just 1. So that's 126. You could also do the other way around. It doesn't matter. You could say 9C4. Make the 4-member group first. And then the remaining 5 people, you put them in the other book, and the other group. That's also 126. You can start from any of the groups. It doesn't matter. Okay. Then it says for a random division into a group of 5 and a group of 4, find the probability that Raman and Sanjay are in the same group as each other. So these are two people. What's the probability that they are both in the same group? Now we have to make cases for this, right? If they're in the same group, we are not sure which group. They could be in the five-member group. They could be in the four-member group. So this is the five-member group. This is the four-member group. One possible case is that they're both in the five-member group. If they are here, then we want to find the probability, right? Probability that Raman and Sanjay are in the same group as each other. Okay. Now we already found the total number of groupings. That's 126. What are the number of groupings that satisfy this condition? So one is in which RS are in the first group. That means for the remaining 3 places, we've got 7 remaining people, 7C3, and then the remaining 4 people, 4C4. That gives us 35. If Raman and Sanjay are in the second group, if they are here, what about this now? We've got 2 places left in this group and 5 places here. We could say out of the remaining 7 people, apart from Raman and Sanjay, we've got 7C5 here. And then 2 people left, that's 2C2. And that gives us the result, that's 21. It's either the first case or the second case. We add them up together, and that gives us the total result. That turns out to be 56. And that's our final answer. Make sense? This is not the final answer. This is the number of selections satisfying this condition. And what's the probability? I think I forgot it when I copied this. What's the probability going to be? That would just be 56 divided by the total number of groupings. That's 126. And that will give the result. You can see whatever that is. Okay. But now let's look at this. In how many different ways can the 8 children be divided? So it's some other different question. In how many different ways can 8 children be divided into 2 groups of 3 and 1 group of 2 to go on the roller coaster? Okay, so how do we think about this now? We've got 8 people. We have to make 2 groups of 3 and 1 group of 2. So we can say those 8 people are A, B, C, D, E, F, G, H, right? We can start from any of the 3 groups. We can say, let's select a 3-member group, 8C3. Then we have 5 people left. Select another 3-member group, 5C3. We have 2 people left. That's 2C2. Now, generally, that's what we would do in this case. Just multiply these. However, there's a complication here. And that complication is, there are 2 groups that have the same size. There are 2 groups that have the same size. They're both 3-member groups. What does that mean? If you have one grouping in which you have 2 people here, GH, ABC here, and DEF here, and another possible grouping in which you have DEF in the first group, ABC in the second group, and GH in the third group. These 2 are actually same groupings. It's the same groups. There's no difference between these groups, between these 2 groupings, right? We've just switched them. The order does not matter. These are both the same. This will be counting these 2 groupings as different groupings. So we have to get rid of this double counting. In how many ways can these groups be arranged? 2 factorial, we have to divide by that to get rid of that double counting. Otherwise, it will be counting these 2 groupings as different. In the previous example, we had one 5-member group and one 4-member group. We did not have this problem in that case. They were both different size groups. In this case, it is selection. That is why the order does not matter. The order does not matter, right? This is selection. The order should not matter. But what this is doing is, what 8C3 into 5C3 into 2C2 is doing is, it is considering these 2 as different groupings. These 2 as different groupings. Okay, it's considering these two as different groupings. So these are not different because they're both identical. There's no difference in them. So we have to divide by 2 factorial because of that. You can try this with a smaller example. So for example, think of making two groups of, we have A, B, C, D. Make two groups of 2 people each, right? Write them down. If you do it directly, that will be 4C2 into 2C2. And that gives you 6. But when you actually start writing them down, what are the possible groupings that you can have? You can have AB and CD. You can have AC and BD. You can have AD and BC. And that's it. There's no other grouping that you can think of. Even if you try writing them down, for example, you can try BC and AD. Isn't that the same thing as this? You can try BD and AC. That's the same thing as this. You can try CD and AB. That's the same thing as this. So in actual, we only have 3 different groupings because these two are identical. These two are identical. And these two are identical. These two are identical. So actual different groupings is only 3 different groupings. This is giving us 6. We have to divide this by 2 factorial because these two are the same. To get rid of that double counting, we divide by 2 factorial, and that gives us 3, and that's the actual answer. We've got only 3 different groupings here. So whenever you have groups like this, in which the size of the groups is the same, you have to get rid of that double counting like this by dividing by 2 factorial. Okay. Just 2-3 more examples quickly. So in the previous case, we did not have equal size groups, right? In this case, we did not have equal size groups, so we did not have to do that. In this case, we did have equal size groups, so we have to divide by 2 factorial because of that. Okay. Now, sometimes we've already discussed this before. I said, let's just do the first part of this. We've got 2 identical cans of green tea, 2 identical cans of orange tea, and 3 identical cans of cola. Find the number of arrangements if the first and the last cans are the same type of drink. Same type of drink, what does that mean? It could be both colas, it could be both green tea, it could be both orange juice. So we consider 3 different cases, one in which we've got C's at the ends, G's at the ends, O's at the ends. Now, when you fix them, again, this is happening a lot in recent papers, they fix some object somewhere. So in this case, the first and the last are the same kind of drink. Now, in the first case, we are saying this is a cola and this is a cola. Now, these are fixed. We don't have to worry about them. We don't have to arrange them anymore because they have to be at those extreme positions, right? At the end and in the beginning. We only have to arrange these middle objects. That's all that we have to arrange. In how many ways can we do that? 5 factorial over 2 factorial and 2 factorial for the first case, and similarly for the others. Add all of them up, you get the total result. So when they fix something like this, you don't have to arrange those fixed objects, only the rest of the objects. Okay. Okay, one last example. And I'll show you that one last one after this. You can just have a look at this, look at that yourself. And yeah, we're just ending. We'll have a break in a few minutes. Just one last question I'll explain. Just a couple of parts of this, and then we stop after that. So there are 9 cards, each of a different color. 9 cards, each of a different color. They are to be arranged in a line. How many different arrangements of the 9 cards are possible? And that's really straightforward. That's 9 factorial. How many different arrangements do not have the pin card next to the green card? You can use the dash and stars method or total minus together because you only have to separate 2. So both methods would work. You can do that as well. Just focus on the 3rd, 4th, and 5th parts. Consider all possible choices of 3 cards from the 9 cards, with 3 cards being arranged in a line. What does that mean? All possible choices of 3 cards from the 9 cards. So from the 9 cards, we have to select 3 cards. Okay. And now those 3 cards are to be arranged in line. In how many different ways can you arrange those 3 cards? Now, out of 9 cards, we have to arrange 3. We could directly do 9p3 for that. Or we could also say, let's select 3 cards and then multiply by 3 factorial, and that gives the same result as well. Any of them would work. You can do any of them. Okay. But now it says, how many of these arrangements contain the pink card? What about this now? Now we've got a problem. Because now we've got a condition. If we have a condition, and the condition is that there should be a pink card there. So that means you have to split it into 2 parts. You cannot do arrangement directly. This would not work anymore because there's a condition on selection. And this condition is that there has to be a pink card there. Okay. Now, if there has to be a pink card, in how many ways is that possible? You say there are 3 cards that you need. One of them has to be a P. So the selection is only supposed to be done for the remaining 2 objects, remaining 2 places. There are 8 remaining cards. Out of those 8 remaining cards, we have to select 2. So that's 8C2. And once you've selected those 2 cards, then you have to arrange all of these 3 cards together. That's 3 factorial. You multiply them, you get 168 from this. You cannot do it directly. In this case, they're talking about arrangements. However, since there's a condition that you want a pink card, you cannot do arrangement directly unless you first satisfy or fulfill that condition that is there on selection. So you have to do it separately, do selection separately, and then do arrangement of that. Then it says how many different arrangements of the 3 cards in part 3 do not have the pink card next to the green card. How many arrangements of these cards do not have the pink card next to the green card? How do you think about this? The pink card should not be next to the green card. How do you think about it? Now, there could be multiple cases. If pink and green card are not next to each other, if they're not next to each other, what does that mean? One possibility could be that the 3 cards that are selected, they do not even have both the cards. So one possibility is that the pink card is not selected and the green card is selected, then they would not be together. Another possible case would be that the pink card is selected and the green card is not selected. In that case as well, they will not be together. Another possible case would be that both of them are not selected. In that case as well, they will not be together. And the 4th case would be that both of them are selected, but still they're not together. They are separated. That's too many cases. It's only 2 marks. Can we make it more efficient? We could say we have found the total number of possible arrangements already. The total number of possible arrangements of the 3 cards, what was that? That was 504. That was the total number of possible arrangements, 504. Out of them, how many have the pink card next to green card? Can we find that case? We can find the difference and that will give us the result. Okay, find the arrangements in which the pink and green cards are next to each other. How can we do that? We could say, first of all, both the pink and green cards have to be selected. Okay, so from amongst the 3 cards that we've got, three cards that we've got, one has to be a P, the other has to be a G. We only have 1 choice left. So from the remaining 7 cards, we have to select 1. So that's 7C1. Once we have selected that 1 card, now after that selection, we've got 3 cards like this in which we want these 2 together. So we put them in a single box. In how many ways can we arrange these 2 boxes? 2 factorial. We multiply by 2 factorial because of that. But then P and G could switch places with each other as well. That's 2 factorial. And that gives us 28. That's the number of arrangements where P and G are together. We want that they are not together. If they are not together, we subtract this number from the total that we found in part 3, 504 minus 28, and that's 476, and that's the final result that we get from this. Make sense? So you have to break it down sometimes in combinations and arrangements separately. Whenever there's a condition in combination, you do that first, and then you do arrangement afterwards. Then there's this other question. This will take a lot of time to explain now. You can have a look at one of those difficult permutations combination questions videos on my channel. You'll find that question solved there. But I'll just show you the solution quickly. You can have a look at this in your own time. These notes are available with you as well. And you can watch the recording slowly as well to go through this if you want, and just scroll down. It's a good one as well. Okay, so that's it in permutations and combinations.